Yeah, okay, so we are talking about how to describe functions in high dimensions, and the functions should be functions on our data sets. And so we have to see, okay, so what we are looking at is functions from R to the P to, let's say, some small dimensions. So let's say R. A neural net is a function of this form, but of course we don't know how to describe it explicitly. But so what we want to understand at the moment is essentially the set of our data. How do we model this? Okay. And up to now I said, okay, our data are given, let's say we take, let's say, the unit ball. And then we said we take the uniform distribution on the unit ball and try to understand probabilistic properties of such functions. We still have to specify which functions, but the idea is that we should have concentration for many functions. So I mean, this set here is a very high dimensional set. But if we take functions, the value in many situations is concentrated close to one value, which then of course is the average value of this. And that's what we want to understand. And we last time we modeled our data by uniform distributions. So in particular, we took the unit ball, said this is our whole set. We normalize and we measure things with the volume. So we normalized it to 1. So we divided everything by the volume of the unit ball and tried to understand what is the volume or the probability of sets which have a given, which we describe in some way by such functions. Okay. And in particular, we had this concentration that in high dimensions, the volume of the unit ball concentrates close to the surface. It concentrates close to the equator, close to any equator. And we also had that two vectors are more or less orthogonal. Okay. And now we want to go more in the direction of maybe more realistic or at least mathematically more manageable data. Namely, we will now, instead of taking a uniform distribution on a unit ball or some other sets, we will now take Gaussian vectors, because those are ones which are maybe mathematically the easiest accessible and the ones which we can really work. Of course, I mean, real data don't have a Gaussian distribution in general, but later we can maybe you start from Gaussian distributions to get other data distributions. And the Gaussian ones are the mathematically simplest ones. Okay, and for those we also want to see concentration. So in particular, we also want to see that, let's say, the length of a Gaussian vector with respect to a Gaussian distribution really concentrates also somewhere. So we want to see the analog of what we saw for the uniform distribution on a unit ball. Okay, and so first I should say a little bit, okay, what do I mean with Gaussian random vector? And I mean, in the new assignment there will also be more on this. So here I will essentially work with the simple situation where all the entries of my vector are independent. Each of them has a Gaussian distribution. But in the assignments, this can be done more general. And then we want to see that we also have some kind of concentration there. And what I'm doing at the moment is essentially that I'm looking on concentration of linear functions. Those are more classical estimates, so this is Chebyshev and Bernstein type estimates. But then later on, we want to see that also nonlinear functions, a big class of nonlinear functions, shows concentration. That's the more complicated thing. But first, we want to start with the linear situation. Okay, so we want to talk about Gaussian random vectors, and we want to understand concentration properties for them, but at the moment it's linear kind of concentration. And names which usually go with this are Chebyshev inequality and maybe also more general Bernstein type. Good. Okay, so I will explain what this means, but let me first talk in general about our situation. I mean, also the situation, what do we integrate, what are our measures, and so. And so, I mean, we are looking on random vectors in R to the P. So we consider random vectors. So I denote my vector with x, little x, and the components I denote by t1 up to tp. Those are vectors in R to the P, but I want to consider them probabilistically. So I have a probability distribution on R to the D with which I measure the probability of events. So the random vector is given by a probability distribution on R to the P, and I assume I really have a density. Of course, I could talk more general about probability measures in R to the P, but let me just do this by densities, because I mean our Gaussian distributions and most things which we consider, I really have a density. Okay, so I have a density in R to the P, which I denote by psi. So this is a function of the vectors of my components of my vector. And I mean that's a density with which I integrate if I want to calculate probabilities of some sets. So this means this density, of course, should be positive. So I mean density always have to be positive. And then, of course, if I integrate over everything the constant function 1, it should be 1. So it should be a probability density. So if I just ask, am I somewhere in R to the P? Of course, I'm somewhere, so the probability of this should be 1. So 1 should be the integral over my density over R to the P. And of course, I mean, this integration is just a p-fold iterated integration with my coordinates. So I can also write it as an iterated integral p times over R. And then I have my density t1 up to tp, and I'm integrating over dt1 up to dtp. Okay, so that's my density. I mean, before, when I looked on the unit ball, the density was just, it was constant on the unit ball and 0 outside. Then I had the uniform distribution on the unit ball, but now I want to allow more general distributions to model more realistic or more interesting things. Okay, and of course this means, so I have my probability density in R to the P, that's all my vectors which I have. And now I want to ask properties about them, and I ask for the probability of those properties. So I want to know what is the probability of some given subsets in R to the P, and I calculate this by integrating with this density over this set. So if I have a subset in R to the P, maybe a set which describes a property of the vectors in which I'm interested, then the probability that my vector is in this set, so that it has this property, of course, is given by integrating just over this set with respect to my density. And of course, this set should be a measurable set. So I mean, this integration should make sense. And of course, a very simple situation. I mean, this is very general. I mean, this density can be anything, and the basic situation where we really can say much more is if the components of my vectors are independent. Okay, so that's a very common situation. At least it's a situation from where we start. Okay, in general, of course, things are not independent, but maybe they can be built out, or you start with independent components. So the coordinates of my vector components t1 up to tp, they are independent if this density factorizes into densities according to each component. So if psi factorizes as a product of psi1 up to psi p, where those are densities just depending on one coordinate. So this here just means that psi, which is a function of p arguments actually is now a product of a function for each of the arguments. So it's a function psi1 of t1 times psi2 of t2 and so on, psi of tp. That's the usual independence, that I have the factorization of my density. Or we can of course also say, what does it mean if I calculate probabilities? If I calculate probabilities of properties which are just given by conditions in terms of each of the coordinates separately, then I have a factorization of this. So the probability that I have two independent events happen is just the product of the probabilities for them. So this means in this setting here, if I have also a set over which I want to integrate, for which I want to calculate the probability, so for sets of my coordinates of the vector, but of the special form that they are only depending on each of the coordinates separately. So if H is H1 cross HP, so where each HI is just a subset of R for all I from 1 to P, then I have a factorization of the probabilities. Maybe that's the more usual way of how you say that things are independent. So maybe let me write down what we have in this setting. So we have so what do we have for the probability that my vector t1 up to tp, first of all, my vectors are always in R to the p, but now I want them to be in this set, and maybe let me write it down what this means. This means that t1 is in H1, t2 is in H2, and so on, up to tp is in HP. I mean, that's what it means, that my tuple T1 up to TP is in this product set H1 cross H2 cross HP. That's just what I'm saying. This tuple is in this set, means first component is here, second component is here, last component is here. Okay, so if I want to calculate the probability of this set, this really means the probability that the first component of my vector has this property H1, the second component has the property H2, and so on. Okay, but now of course I can use my formula for calculating probability. So I'm integrating over my density. So this here is now the integral over this set here, H1, the product up to HP, and I'm integrating over psi of T1 up to TP, dt1 up to dTP. I mean, that's my general formula, and if I don't know anything else about psi, of course, okay, it doesn't make a difference whether I integrate over such sets or not. But now, if my coordinates are independent, then this here factorizes into psi of T1 times psi of T2 times psi of TP, and then of course the structure here goes nicely with this, so I can now do this integration here in an iterated way. So I'm integrating over T1, and this affects only this, and I'm integrating this over H1. Then I integrate over T2, this only affects this, and I'm integrating over H2. And then the whole thing factorizes into the product of the corresponding integrals over for each of the coordinates. So what I have here is then the integral over H1 psi T1 dt1 times the integral over H2 psi T2 d2 and so on up to the integral over HP psi TP dTP. Yeah. Okay, and now of course those integrals are now probabilities for each of the components with respect to the density which belongs to them. Okay, so this is the probability that the first component is in H1. This is the probability that the second component is in H2, and so on. So here really we see that, okay, probably what everybody knows or has seen before, that the factorization of my density really means that probabilities of independent events also factorizes. So maybe this here is now the same as the product of the probabilities of events where I only make a statement about one of the components. So this is the probability that T1 is in H1 times the probability that T2 is in H2 and so on times the probability that Tp is in HP. So the probability that I have a vector where I require that the first component has this property H1, the second component has this property H2 and so on, factorizes into the product of the probabilities that T1 has the property H1 times the probability that T2 has the property H2 and so on. And of course these psi's here, the psi i's, are probability distributions on R. So they are densities for each of the components. Okay, so in particular this means if I'm integrating over this guy here over the whole R, then of course I also get 1. The total probability, actually this here should be a psi 1, psi 2, psi p. So this factorization, they all have indices. So here also, psi 1, psi 2, up to psi p. Good. So this is just, I hope this is clear. Everybody should have seen such things. So I mean, we have, in principle, we have random vectors which are given by densities. They can be quite arbitrary, but if they are arbitrary, we cannot really do much concretely. Okay, and situations where we can really deal with are where actually the components of our vectors are independent. And that's what I want to do in the following. So first of all, that they should be independent. And then, I mean, each of them should have the same distributions. So all this psi 1, psi 2, and so should be the same distribution. And then, of course, I want to take the nicest distribution which we have for a one-dimensional random variable, namely the Gaussian distribution, which is very important from a theoretical point of view, and which is also very accessible for concrete calculations. Okay, so in the following, now we want to get more specific. So we consider now our Gaussian random vectors. And those are given where the coordinates are really independent. And they are actually also have all the same distribution. So that's what usually is denoted by ID, independent and identically distributed. So just, and the distribution should really be the Gaussian distribution. So standard, and it should be a standard Gaussian, about which we already talked in the first assignment. So we understand a little bit about this. Good. Okay, but then I think I'm ready to write down the definition of our standard Gaussian random vector, the one which we want to consider in the following, and for which we want to show concentration stuff. Okay, but so let me first define it very precisely by really giving you precisely the density. But in principle now, after this, we know what it should be, because I mean we know what is the density of a Gaussian one dimension, and if we just have independent copies of them, we know that we should just take the product. So in assignments, which came up just 2 days ago or so, I mean we will also look on more general Gaussian random vectors, but here I will restrict to the simplest version. And maybe later we will also go to random vectors where the mean and the covariance are more general. Good, but for now we restrict to the standard case, the simplest situation which we can have in p dimensions for a Gaussian random vector. And so that's what I call a standard Gaussian random vector. A standard Gaussian random vector is what I more or less said before already. So this is a vector in R to the p, and as usual I denote the components of the vector by t1 up to tp. So this is given by a probability distribution. So this is given by a probability distribution, a density, such that we have what I said before. We have that all the coordinates are independent. So all t1 up to tp are independent. And they are all identically distributed, and they all have as their distribution the standard Gauss distribution, which means mean 0 and variance 1. So each of them, so each ti has a standard Gaussian distribution. So which we denoted by n 0, 1. So this means it's a Gauss distribution with mean 0 and variance 1. And of course we can write down the density. I mean, that's what we did in the assignment, and where you also calculate moments of this thing. So this means the density for each of them, so psi for ti, the density for the ith coordinate is given just by this normal distribution, which is e to the minus t squared over 2, and then you have to normalize it by 1 over square root of 2 pi e minus ti squared divided by 2. That was the density of the Gauss in one dimension. Good, and now of course we have, if I now want to write down the density for my vector, because the coordinates are independent, I just have to multiply all those guys. Okay, so what we get is thus that now the distribution for my random vector, which is the density for all the p coordinates, this is just the product of the density for the first coordinate times the density for the second, and so on, up to the density for the last one. But each of them has this distribution here, and so this means just collecting now terms. So each of them has a factor 1 over square root of 2 pi. So we get this p times. So what we get is 1 over, we have this 2 pi, we have it p times, but each of them is a square root, so it's 2 pi to the power p over 2. Okay, and then we are multiplying the exponential guys. So we have then the exponential, so each of them has a minus 1/2. Okay, and then I mean the product of the exponentials gives us of course the exponential of the sum. So we have here t1 squared plus t2 squared plus tp squared. Good. Yeah, and now we see that actually, I mean, what we have here, of course, is a very nice vector quantity. So namely, this is just the square of the length of my vector. So I mean, I can also write it directly in terms of the vector, important quantity of the vector, which shows you quite a bit. I mean, that it really is not just it's not just anything in the components of the vector, but it's really something which takes in, which depends on maybe the most or even only real property of a vector, namely its length. So this here is the length of my vector squared. So I can write this directly by not going back to the components, but in terms of the vector itself. So it's 1 over 2 pi to the power p over 2. And then I have e to the minus, and then it's the length of the vector squared divided by 2. That's the density of my random vector. So if I want to calculate any probability for some properties of my Gaussian random vectors, I have to integrate over this density. Okay, and so we denote this as before. We use this shorthand notation. If we want to say that a vector has this distribution, so we denote this by saying x has a distribution, and we write again n for normal distribution. Gaussian distribution, normal distribution is the same. And then we put here a mean vector. So here the mean are 0. I'm talking not about the mean. And here we're putting a covariance matrix. Here the covariance matrix is just the identity. It just means that all components are independent and each of them has variance 1. So I'm putting here the identity matrix, the p times p identity matrix. Okay, I mean, here maybe it's not so clear what this means, but in the assignments, I mean, we define more general Gaussian random vector where you have a vector here, a mean vector, and you have a covariance matrix here. And of course we see how this is related with this situation. Of course you can transform essentially one into the other. Okay, but this here is somehow the simplest one. And okay, so maybe I should say this here is a vector of means in general. So it's a vector, but here it's just a 0 vector. So it's a vector in R to the p, and this here is a matrix, the covariance matrix. It's a matrix of the covariances between all my entries, matrix of covariances. And here it's just the identity matrix. So this means a p by t diagonal matrix where I just have ones on the entries. Good. Okay, so that's my situation of my random vectors, with which I want to understand how they behave in high dimensions. And yeah, actually, in the first assignment, I mean, you modeled essentially this situation, and you should have seen that there is concentration. So, for example, you looked on the norm of a vector with respect to this distribution in the histograms. You saw that this essentially concentrated about something, and the something was the expectation value. So that was in the first assignment, and now we want really to try to prove this, or see how can we prove such things. Okay, so yeah, so so what have we seen on? Yeah, so in numerical simulations we have seen concentration we saw it for the norm, but we also looked on the infinity norm, which is a more nonlinear object, and so the idea is that actually for quite some class of functions we should have concentrations. So what we expect, and where we at least hope to be able to prove something in this direction, so we expect concentration for this situation. So this means if I calculate the probability of my random vectors, my Gaussian ones, and I have a function, then this function applied to my vectors in most cases should be the same, more or less the same. It should be close to one value, and this value, of course, has to be the expectation value. So what we want to compare is the value of f of x with the expectation value. Okay, and the difference between this and the expectation, this should be small, or to say it another way, the probability that this is not small should be large. So we expect the probability that this difference is, let's say, bigger than epsilon, that this should be small, at least if the dimension is high. I mean, in small dimensions, I mean, okay, I mean, we have probabilities for everything and they don't really concentrate, but in high dimensions they should concentrate. So the probability that the value of my function has a distance to this constant value here, which is not small, that this probability should be small. To be small. if the dimension is large. And of course I have here a function, so I should specify which functions. And the idea is this should be true for a quite big class of functions. And of course they need some properties. Of course it's not true for any function. Because I mean we can, for example, pick out just single. If I take as a function just looking on the first coordinate, I mean this first coordinate is a Gauss, and this does not concentrate around its mean, even if I have more and more other coordinates. So it should of course be functions which take into account all variables on a similar level. Good, okay, but this is something which we make more precise later. But it should be nice classes of functions. And what we mean with nice, this we still have to find out. I mean, this will be this class of Lipschitz functions. Okay, so this is still to be determined. And maybe first we are looking on linear functions, where essentially we are summing over the components, because that's something which we can control much better. In particular, if we also have independence in the background. Okay, so I mean, this is a quite big program. So I mean, we want to understand this, and first we want to understand it more for linear functions, where it's more traditional, quite well understood stuff. And then later we also want to see that it's for much bigger class also of nonlinear functions. Those are Lipschitz functions, and that's maybe more modern concentration theory a la Talleyrand and so on. This is also very powerful. So also for nonlinear functions we have concentration. And I mean, of course, nonlinear function is what we have in neural nets or so. Just having concentration for linear functions is maybe not so useful, but that we also have it for a big class of nonlinear functions. That's very very important. Okay, but so maybe let us try to look on taking the length of a vector. So let us try to prove concentration for the length of a Gaussian random vector. At least there we saw in histograms that it concentrates. Okay, so we consider as our function here. We consider f of x as, let's say, maybe the best thing is the square of the x, because then this f on x is really the sum of those guys which are independent, so it's really a sum of independent things. That's something which there's hope that we can control it. Okay, and then of course, in concentration, of course, we want to compare the value of the function with a constant function, which usually should be the expectation. So you should also be able to calculate the expectation. And in this case, this is very simple. So if I'm looking on this function, then the expectation of this function, so the expectation of x squared, so this of course is the expectation of t1 squared plus t2 squared plus tp squared. And now, of course, the expectation is linear, so it's just the sum of the expectations of each of the square of the coordinates. But I mean, this is just the second moment of each of the coordinates. So this is the expectation of t1 squared plus and so on, the expectation of tp squared. And for this, I don't need any independence. This is just true. This would be true for any vector. And now it's just I just have to know what is the second moment of each of my coordinate. The coordinate has now a Gauss distribution. The first moment is 0, and the variance is then the second moment. So this is just 1. So each of them is 1. So I have here just p times 1, which is p. So the expectation of my Gaussian random vector of p squared, of the square of the length, is p. Okay, and so this means that the square of the length of my vector should be close to p in high dimensions. I mean, that's what we observed in these pictures. Or maybe if I forget the square, this also should mean that the length of the vector is close to the square root of p. if we have concentration. I mean, this calculation here, of course, is easy. So it's easy to see what is the expected value, but concentration tells me that for most vectors, I'm close to this value. That's what we expect. That's what we saw in the histograms, but that's something which we also want to prove. Okay, so we expect that the square of the norm is close to P, and this means we probably should also expect that the norm itself is close to the square root of P. Okay, but of course, okay, being close to something and then taking the square root might not be so clear whether this is okay, but this is okay here as we still will soon. So we also expect concentration of the norm of the length of the vector to the square root of P, but maybe you should observe that the expectation of the length of the vector is not the square root of P. So I mean, it's much easier. I mean, it's easy to calculate the expectation of the square, because then it's just a sum. But if I take here the square root, then I don't really know what I should do with the expectation. Okay, so this is not the expectation of the norm, but of course it will be close. And if P goes to infinity, they will asymptotically agree. But this means in such concentration estimates, maybe comparing things to the expected value is not always the best thing, because you are not really able to calculate precisely the expected value. Maybe there are other quantities which asymptotically are the same, and for which you can work much more easily. For example, you can take the median of a distribution. That's a point where half of the probability lies on one side and half lies on the other side. And I mean, this is not the expected value, but in high dimensions, if things concentrate, the median and the expected value are not very far away, and asymptotically they are the same. But maybe the median is easier to handle. So this just means, in principle, you have concentration with respect to the expected value, but if you're not able to calculate this might not be so useful. Yeah. First thing you try to calculate the expectation, but maybe this is not so clear. So or you cannot do it. But then maybe median or other quantities which asymptotically are close are much easier to calculate, and then maybe it's better to write your concentration inequalities in terms of those other quantities. Good. Okay. So that's what we want to do, and let's see how far we can go. Yeah, and so let us maybe try to prove. So now I want to do, let's say I want to do now concentration of the length of my vector by comparing it with the square root of P, which is not the expected value, but still in large dimension it should be close to this. So that's maybe the theorem which you want to prove. And let us try to see what do we need for this. But so let me first write down the theorem, so that we really see that we have a theorem, and what is the nature, how does it, what kind of concentration do we have. But then, we have to develop some machinery for really proving it. But this shows somehow the general machinery for proving such concentration. Okay, but so first let me write down the theorem. So that's what we want to prove. So that's a precise statement that the square root, that the length of a Gaussian random vector should be close in high dimensions to the square root of P. So we consider a p-dimensional standard Gaussian random vector. So X has a distribution, a normal distribution, Gauss distribution, which means 0, and covariance 1. So that was the one which we had before. All components are independent. Each of them has the standard Gauss distribution. And then I'm claiming then for an epsilon, which is between 0 and square root of P, So I want the probability of the vectors in R to the P for which the length is not close to P. So the distance between the length of the vector and square root of P, let's say, should be bigger than epsilon. So we're looking on the probabilities that we are far away from this guy, and this probability should be small. And what we really would like to have are exponential estimates. So if we want to estimate this, so this is the probability which we want to estimate. This should be small, and it should be smaller than 2 times. Yeah, that's what we want to prove. E to the minus epsilon squared by 16. Okay, and maybe if I write it like this, epsilon usually is a very small number, but here, of course, if epsilon is small, I mean, then this is close to 1. Then, of course, small has to be seen here as small compared to P. So, I mean, if P is going to infinity, this here grows like square root of P, but epsilon should be just a constant number, 5 or so. Okay, and maybe here writing epsilon is a little bit misleading, so maybe let me rescale things so that if I go with P to infinity, the expected length is kept constant, let's say 1. So I rescale my normal distribution so that it has variance 1 over P, so that the expectation here is not P, but 1. And then, of course, I can look what is the probability for having a distance from 1 which is smaller than epsilon, and then epsilon can really be a small number. So maybe here calling it epsilon, if you see epsilon you always think it really should be a very small number, but of course you have to small here means it should be small compared to this guy. Okay, so maybe it's better to do the rescaling. So in the rescaled version, where I replace my random vector by a rescaled one, where I rescale everything by 1 over square root of P, which has the effect that the expected that the square root of P here, so I divide now here everything by this, and then of course this here gives a 1. So this means in this rescaling the norm should concentrate about 1, independent of P. Maybe that gives a better idea. That's maybe what you really want. If P goes to infinity, maybe you should keep the thing in which you're interested, you should keep this constant, so that it doesn't explode. Okay, so we rescale this. Okay, and let me also denote the components of the x tilde by t1 tilde up to tp tilde, and then of course the x tilde has still independent components, but now each of them has a rescaled Gaussian distribution. So the ti's are id, or the ti twiddle, and the distribution of them is a normal distribution, a Gauss distribution, still this means 0, but the variance is now 1 over P. Okay, but anyhow, so if I rewrite this here essentially by dividing everything by the square root of P, and then also replacing here the epsilon by epsilon divided by square root of P, I get that the probability of those rescaled random Gaussian vectors, probability that the norm of those guys has a deviation from 1 which is bigger than epsilon, that this is smaller than 2 times the exponential. And I mean, what was here epsilon? The new epsilon is epsilon divided by square root of P. So here I also, on this side, I also have to do this, or actually it is no, I mean, I have here I have to replace epsilon by epsilon times square root of P, so that after division I get the epsilon. So here I have to replace the epsilon squared by P times epsilon squared divided by 16. Okay, now you see, now I can take a small epsilon. Okay, but then if the p is getting big, then the epsilon squared will be outweighted by this p for p large, and then this will become a large quantity, and then I have an exponential decay. So here I really can fix epsilon independent of p. So I say I fix this epsilon, and then if p goes to infinity, I have exponential concentration. And maybe in this form you also see, if you want to see where am I sitting, in which neighborhood of the norm, I mean that's where this quantity here is constant. So if you choose epsilon in the order of 1 over square root of p, that's where essentially if you increase the dimension where your mass is more or less shifting to. Okay, good. So I mean that's a statement which we want to prove. And I mean in the histograms, I don't know, yeah, okay, yeah, we didn't really compare it with precise estimates. In some of the assignments, I gave you kind of concentration inequalities, and you compared it to this. So maybe you can also go back and try to compare the histogram of the norm for the Gaussian vector with this one. But of course, the main point now is that we have to prove it. So how can we prove something like this? And let us first get started. And maybe the first problem is, I said if I'm looking on x squared, then I have the sum of independent guys. That's maybe which we can do. The norm itself is the square root of this, so this is very ugly to deal with. So maybe this concentration here for the norm, we really should transform into a concentration for the norm squared, because the norm squared looks much better. And that's the first step, which we can now do right away. I mean, even though we want concentration for the norm, we are actually doing concentration for the norm squared. Because we can compare those guys quite easily. So this is the proof, but only, I mean, the first part getting started, where we reduce the norm to the norm squared. And then with the norm squared, we have to see what we do there. Okay, so what we want is the probability that the norm of x minus square root of p is bigger than epsilon. Okay, and now I compare this with a corresponding estimate where I compare the norm of x squared with p. But how can I get from here to x squared minus p? Yeah, by just multiplying this guy here with the norm of x plus the square root of p. And I can estimate those guys. So maybe let me write down here the probability of the situation when I'm looking at the norm of x minus square root of p. That's something which is hard to deal with. So I want to take the square of those guys, and I can do this by multiplying this with the norm of x plus the square root of p. So if I multiply this, I will get norm of x squared minus p, which is the easiest thing. Okay, but here, I mean, what is the estimate now? I mean, what I want is that this guy is bigger than epsilon, and now I multiply this with something which is always true, independent of x. I mean, this guy here is always bigger than the square root of p. So if I write it like this, then I have that whenever, let me see, whenever this is true, whenever I have this inequality, I also have this inequality, because I just multiply this inequality with this, but then this guy is bigger than this. Okay, so this here, let me see, is this correct? Yeah, I want estimate in this direction. Is my argument correct for this direction? Yeah, so whenever I have this, I also have this, but I might have this in more situations. Okay, so the set for which this is true is a bigger set than the set for which this is true. So the probability of this set is less or equal than the probability of this set. Because whenever this is true, this is also true. So this event here is a subset of this. Yeah. yeah, the absolute value should still be there. Or maybe here. Yeah, okay, but I mean this product here, so this is now the absolute value, so I mean I get here the square, and I get here the square of the square root of p, so I get here this. And so now you see here I have now the corresponding concentration inequality for this, the square of the length. But here was a change. So you see, I mean, if I want epsilon here I have something else. Okay, so let me write it again. So this is the probability of the event where the norm of x squared minus p absolute value is bigger than epsilon times the square root of p. Good. Okay. So if I want to show that I can estimate this in this exponential way, but I will do this by showing actually that this here can be estimated by this. So I do now the concentration estimate for this quantity with respect to this, and then I also get it for this one. And I mean this shows in general how I can, if I know something for the square of the norm, how I can go back to the norm itself. I mean, yeah. Good, but now, okay, I mean, now we have to prove this. And so why should this be easier than just the norm? Yeah, because the norm squared is the sum of things which are independent. So, okay, so we have reduced. Yeah, so we reduced concentration question for the norm. For the norm of x to a concentration question for the norm squared. Good. Okay, and the norm squared, this is easier. At least we have hope that it should be easier, or we can deal with it, because the norm squared is the sum of the square of the components, and those components are independent. Okay, so essentially this is now a situation where we are looking on a function which is actually, I mean, which is a sum of independent guys, and that's a situation, yeah, which we should now address in general. This is something which we can deal. I mean, we have a sum and we have independent quantities. Good. Okay, so now I switch maybe first to a more general situation, to inequalities, which we are going to use. First of all, very general, where I don't bother about whether it's a sum or of independent things. I mean, there are Markov and Chebyshev inequality, which are very general, which are always true, and which applied in the right way will also be very useful for such situations. But maybe I first should tell you, or maybe recall, what Markov and Chebyshev inequality are. They are just for just one variable. The variable doesn't have to be a sum of anything or so, but later we will apply to such situations. Okay, so I mean I will come back. Okay, so I mean the proof just started. I mean we interrupted here, and of course I have to come back to it later. But first we have to calculate or to develop some tools with which we can address sums of independent random variables. Yeah, and the first very general inequality is a Markov inequality and then a Chebyshev. And I mean, they are inequalities which gives us some information about what is actually the meaning of the expectation and the variance of a distribution, what information is contained in them. In particular, information about how much can the distribution be spread out. I mean, concentration means our distribution should narrow in some sense. But the expectation and the variance tell us that they cannot be spread out too much. Okay, so the first one is a Markov inequality. This is about expectation. Okay, and this is now about general, let's say, random vectors. Let me call them y now. I mean, x is our Gaussian random vector, to which we will come back later. But now I will do some general statements, so maybe let me denote the general random vectors, where we don't make any specific assumption how the distribution looks like. Let me call them y. So let y be a random vector in R to the p, be a random vector with probability distribution. Okay, I mean, I still call it psi. It should have an arbitrary probability distribution, but I'm not assuming that the components are independent or so. And now I want to look on a function of this vector. And so let me call this f. So f is a function from R to the p. But now, for the expectation, somehow I want positive functions. So I mean, the idea is, I mean, the expectation of a distribution, I mean, how much does it tell me whether this distribution can be spread out or not? If my variable can take on positive and negative values, then of course things can cancel. Also, I mean, I might have a distribution where the expectation is 0, like the Gauss, but of course there can be very large values, and the expectation cannot control this. But if my variable can only take on positive values, I mean, then if I have a fixed expectation, then there cannot be too many values which are very, very much bigger, because I mean they cannot be compensated anywhere. So if I have very large values with quite some probability, then the expectation value must also be quite high, if they cannot be compensated by negative values. Okay, and that's what Markov inequality tells us. Okay, but so this means here I really have to consider a situation where my function only takes on positive values, so that I don't have cancellations. Okay, so this should be a positive function. And then, then I can control the deviation, or now I'm not controlling anything to the average value, but I just ask the question, what are the probabilities that I see large values of my function? And this I can control in terms of the expectation. So then for any alpha bigger than 0, we have the probability of my vectors in R to the p such that f of y is bigger than alpha. This can be estimated by the expectation of this function f of y divided by alpha. So this means the bigger I make alpha, the smaller this gets. So the probability that I see very large values is getting smaller and smaller. So that's a very basic inequality. I mean, it's very simple and easy, but it gives you the idea that if you are looking on moments, I mean, this is the first moment. Moments contain some information about the spread of your distribution. Okay, but this is a bit specific because you need positivity. Okay, but later, Markov inequality will actually be the basis for many things which we do later, because we apply it to specific other functions, which we build out from the functions in which we are interested. Okay, so let me give the proof. I mean, the proof is quite simple. So I mean, if you had, so I suppose in mathematics for computer science part 3, at least something like this probably should have seen. But if not, let me just do it. Okay, so I mean, essentially we start from here. So we calculate, we write down what is this, and then we want to do an estimate which gives us this. So let me start with the expectation of my function f of y. So what is this? I mean, by definition, of course, this is just I take my function f of y, and I'm integrating over all y's with the density over all of Rp. I mean, that's what the expectation is. I take my function and I'm integrating with respect to the density of my vectors. Good. Okay, and now the idea is that this integration here is over everything, but now I decompose this integration into the y's which satisfy this and the other y's. And then I can do estimates. Okay, so I write this integral here as a sum over two sets. Namely, first I'm integrating over the set in which I'm interested. That's the vectors where the value of my function f is bigger than alpha. So here I'm integrating over y, for which f of y is bigger than alpha. And I'm doing the same integral, of course, fy psi y dy. And then I'm integrating over the rest. So I'm just decomposing r to the p into two sets. A set and its complement in the integral over all r to the p is, of course, the sum over those two sets. So here I'm integrating over the y's for which this is not true. So this means those are the y's for which f of y is less than alpha. And I'm still integrating over fy psi y dy. Okay, and now, I mean, here I know something about f of y. This is good. I can estimate. Here I know something, but the estimate goes in the wrong direction. Here I cannot really estimate making a direct estimate by using something on f. But what I use is just I'm integrating here positive functions. I mean, the density is positive, and f is also positive. That was my assumption. So I'm integrating a positive function over some set, and what I get is at least a positive quantity. So this here. So I'm not using much. I'm just using here that everything is positive, and I don't care about how big or how small this is. At least it's bigger than 0. So this is greater or equal than 0, because I mean the density, of course, is always bigger than 0. But I also assumed here that my function f, in which I'm interested, is bigger than 0. Yeah. Oh, because I assume I'm dealing here with measurable functions. Okay, that's okay. So I mean, of course, I should here, if I say here a function, I mean, I assume all my functions are measurable, and then if you define sets in terms of the function, pre-images of your functions, then those are measurable sets. So okay, I mean, those are the things which of course, we should have in the background. So we use some kind of measure theory, but just saying, I mean, all the integrals we are doing are okay and valid. So I mean. Okay, I'm not writing down that my functions are measurable, but that's what I always mean if I talk about such general things. Okay, so this is bigger than 0. So if I just throw away this term, then this quantity here can only get smaller. So what I have here is greater or equal than just the first term. The first term is the integral over y, fy bigger than alpha, fy cy dy. And now on this set, I know that my function is always bigger than alpha, so I can estimate this function against alpha. So I can say this is bigger than if I'm integrating just the constant function alpha instead of f of y. So here, let me write it like this. So it's the integral y where f of y is bigger than alpha. And on this set, I can compare f of y with alpha. So I'm just integrating over alpha cy dy. And now, of course, alpha is a constant. I can take it out. And then I'm just integrating over this set with my probability distribution, which gives me just the probability of this set. So this here is now just alpha comes out. And the integral there is just the probability of the y's for which f of y is bigger than alpha. Yeah, now you see I have exactly what I want, because now we should read it the other way around, namely this probability here, I divide by alpha, is smaller than the expectation divided by alpha. Okay, so this is a very basic inequality, but it tells me that the expectation contains, at least for positive functions, quite some information about very big values. They cannot occur with too high probability. Good. Okay. Yeah, so that's a basic inequality. But in our context, this is not very useful. I mean, because, so what do we need here? I mean, our function, which we consider here in this context, that would be this function, the absolute value of this. And I mean, we cannot calculate the expectation of this function, in particular because of the absolute value. I don't know how to deal with the expectation of an absolute value, because there's no algebraic way of dealing with this. Okay, so this is a basic inequality, but in our context it cannot be used for anything meaningful. Okay, but so let's go a step further. Namely, let's now see, okay, the first moment tells us something about our distribution, so let us look on the second moment, or maybe better on the variance. That's Chebyshev inequality. And Chebyshev inequality is really now going in the direction that it tells us something about the deviation of my variable from its mean. And this can be controlled in terms of the variance. I mean, this is just this general idea that the variance tells you somehow how spread out your distribution is. So Chebyshev is just making this precise. The variance is really something about the width of your distribution. If you have a small variance, it means you have some concentration. So in principle, concentration in high dimension, you can do it maybe by trying to see that the variance of your quantities are going to 0. So, but we will, okay, do it even more general. Okay, but so let's do Chebyshev. Also very simple. And actually, Chebyshev follows from Markov if you do it in the right way. So in principle, Markov is at the base of everything. You only have to apply it in the correct way. But Chebyshev is often much more useful. So, okay, I think we are not coming back today to the proof of this. We first have to develop some tools, but next time, of course, we will come back to this theorem. Chebyshev inequality. So there we assume, maybe, okay, I mean, I didn't say here that the expectation should be finite. Of course, it could be that the expectation is infinite. Then it's still true, because then it's not saying much. Okay, in Chebyshev, I mean, I should assume that the expectation and the variance are finite numbers. Okay, so let y again be our random vector in p dimensions. So be a random vector again with quite arbitrary distribution, no specific assumption on independence or so. And we consider again a function from p dimensions to r, but now there's no positivity assumption. Now it can be an arbitrary measurable function, and I assume that the expectation and the variance of it are finite. So function such that, I mean, the average, the mean, the expectation, so f of y, this is finite, and then also the variance. I mean, the variance I denote by v, so the variance of f of y. So I suppose everybody knows the variance. So this is the, I mean, one way of writing it is the expectation of f of y minus the expectation of f of y. So I'm comparing, I take the expectation of the comparison between the value and the expected value. And I take the square of this. Okay, this. The square of this, or I can write it just as the expected value of the square of my variable, which is f of y squared, minus the square of f of y. Okay, just multiplying this out, this is the same. Okay, so suppose everybody knows the variance. So in particular, if my mean is 0, of course the variance is just the second moment. Good, I assume those guys are finite. And then Chebyshev gives me exactly an estimate of the form which I'm really after, namely telling me probabilities of the deviation of my function from its expected value. And it's exactly the variance which controls this. So then, for any epsilon greater than 0, the probability of the vectors in R to the P for which the difference between f and f of y and the expected value of my function f is bigger than epsilon, this can be controlled by the variance of my function f of y divided by epsilon squared. Okay, so that's really, this looks like something which we really want. We want to compare a typical value or general value of my function with its expected value, and we want to control it. And here we have a very general, I mean, again, this doesn't use any independence between the components of y or anything. So it's just telling us the very general principle that the variance controls how much your distribution is spread out, but in a precise way. So if epsilon is here getting bigger and bigger, then this is getting smaller and smaller. So if you have a small variance, I mean, if epsilon, again, I mean, if epsilon is or epsilon squared is much bigger than the variance, you have small probabilities of finding something which is so far away from your expected value. Yeah, and the proof of this is just reducing it to Markov. Essentially applying it to this function here, but this function here has this problem of having the absolute value, which is not easy to deal with. But then there's this idea in the game, I mean, if you want inequalities, we can get rid of the absolute value or things like this by squaring it. Okay, and the inequalities are preserved. So that's what we are doing here. We are looking actually on the square of this. We apply Markov to the square of this. So the proof. So we will use Markov, but for which function? For the function that we call it g, which is actually not this here, but which is the square of this. And this gets me rid of the absolute value, which is hard to deal with. So for g, so g is by definition f of y minus the expected value of f of y and the whole thing squared. Good, and the good thing is that this g is really a positive function. For Markov I need a positive function. So here I take the square of something, so this is positive. So g is a positive function. And yeah, what is the expected value of this g? Yeah, what is this? Expected value of g this is exactly this. So this is exactly the variance. So you see, I mean, Markov needs the expectation of a function, but with this g, the expectation is exactly the variance of my function f. So that's good. That fits together. So this is really the variance of my function f of y. Good. And now we can use. Now I use Markov. Or let's see how we use it. So I have epsilon bigger than 0. And what I want, okay, I mean what I still want, is the y's for which the absolute value of f of y minus the expectation of f of y is bigger than epsilon. Okay, I mean this is something which is hard to deal with because of the absolute value. But now I say, okay, instead of looking on this inequality, I just square it on both sides. Squaring is monotone, so I mean the inequality is still the same. So I can say this is the same as looking on the square of this is bigger than the square of this. So this is the same as the probability of the y's, for which now the square of this, and this is f of y minus the expectation of f of y squared, is bigger than epsilon squared. Just squaring it. Yeah, and now I mean, this is now my function g. So I have now really a positive function, and I'm asking for the probability that this function is bigger than epsilon squared. And that was what Markov was telling me. So namely, I can estimate this by the expectation of this function divided by what I have here. Before it was alpha. So the alpha is now epsilon squared. So this is less than the variance of this function here. G of, no, the expectation. Markov. So here I'm using Markov. I take the expectation of this and divide it by what I have here, which is epsilon squared, but the expectation of G is just the variance of f. The variance of f of y divided by epsilon squared. And that's hopefully what Chebyshev was claiming here. And now you also see why I get the square here. In Markov I had just a linear 1 over alpha, but this is because I do this one step where instead on looking what I'm really interested in, I'm squaring this. And then I go back to Markov. Good. Okay. Yeah, and maybe we can now check whether in our case of the Gaussian random variables this gives us something. Because I mean this is really a statement which should tell us, I mean, if we take for f now the norm squared, then we can calculate this here, and this is exactly what we want, and it should give us something. Okay, it will give us something, but it's not as strong as what we really want in the end. So I mean, Chebyshev is good. In many cases you can use it, but actually one can do better if you really use the full power of having independent and also Gaussian variables. But let us first check what it tells us here. Okay, so use this for our Gaussian vectors. So for our Gaussian random vectors. So now the y's are again the x's, which had this Gaussian distribution, the standard Gaussian distribution, and of course the function was the function where we take the square of the length. So f of x is the square of the length of our vector, and then we already know, I mean, so this is a situation to which I can apply Chebyshev, and of course we know what the expectation of this function is. So I mean that's what we already did before. I mean the expectation of f of x is the expectation of x squared, but the expectation of x squared, this was the expectation of the sum of the t squared, and this just gives p times the expectation of each of them, and for each it was 1. So this was just p. I mean that was what we know. I mean that's so really the expectation of this is p, and we want to compare what is this. Okay, and we can use Chebyshev if we can calculate the variance of this guy. So the variance of the norm of x squared. So this is the variance of, I mean this is as before, it's the sum of t1 squared up to tp squared. Okay, and now we can use the fact that the coordinates are independent, and the variance of the sum of variables is the sum of the variances. So I mean you can also check this directly more or less by using this and basic properties of independence. But I hope this is something which everybody knows or at least believes. So the sum of the variances is the sum of the variance of those guys here. So this is t1 squared plus and so on, plus the variance of tp squared. And here I'm using independence. For this I have not used independence. That was just linearity. I mean this here I didn't use the fact that the components are independent. But here, I mean the variance is only linear if I have independent variables. So there I use at least a little bit of the special structure which I have for my Gaussian variables. Good, so I have here the variance of each of the components, and so I should calculate the variance of the square of a Gauss. So this is not the variance of a Gauss variable. I mean the variance of our Gauss distribution is 1, but here I'm taking the variance of the square, which of course we can calculate. So maybe let me write it down. So the variance is the expectation of the square, what I have here. Let me just call it t. But the square of the square is t to the power 4. And then I have to subtract the expectation of this variable multiplied with itself. So it's here the expectation. This variable is t squared, and I take this squared. Good. Okay, and so this is the fourth moment of a Gauss, which is 3. And this here is the second moment, which is 1. So this is 3 minus 1, so it's 2, what we get here. So each of those guys gives 2, and I have it p times. So I have here 2p. Okay. Yeah, I mean this calculation maybe you should do it by yourself just to convince yourself, but it's just using a bit of independence, and of course you see low moments of Gauss. For the variance here, for this calculation we have to know at least the fourth moments of Gauss. Yeah, okay, but then we have a precise formula for the variance, and then we can just write down what Chebyshev tells us in this case. So Chebyshev is now an estimate for something which we really want. So what is the probability of our Gaussian random vectors for which the difference between the square of the length and p is bigger than, now I erased it in this form, actually we wanted bigger than epsilon times the square root of p. I mean, if without here I wanted an estimate in epsilon, but we have seen that if I should do the estimate for the square of the norm, we should compare it with this one, because then this corresponds to the epsilon which I had before. So anyhow, that's what I interested in my estimate. And so Chebyshev tells me, yeah, okay, this is less than, I mean, this here is the expected value of this. Okay, so then this is less than the variance of this function here, which is the square of the norm, and I have to divide it by the square of this here, which is epsilon squared times p. Yeah, but the variance of my square of the norm was 2p, so this here is 2p divided by epsilon squared p. The p's goes away, so I have 2 epsilon squared. Good. Okay, and so we see we get some estimate in epsilon, but I mean what we are claiming is that we have an exponential estimate. So I mean what we want is something like e to the minus epsilon squared divided by, I don't know, 16 or something like this. Okay, and so we get something like this. So this is quite far away from what we really want, but it's already a concentration. It tells us something, but the concentration is not really as strong as we really expected, and as we can prove if we involve more advanced or maybe more information about our distribution. So maybe you have seen the idea was Markov is looking on the first moment, Chebyshev is looking on the second moment or the variance, and of course you can ask, well, can I use higher moments for giving me more concentration? In principle, that's what we are going to do, but if you want to try to do it directly with the moments, it's getting quite complicated. So what you usually do is that you take the generating series in the moments, which is more or less the Fourier transform, and you formulate it in terms of this, because this contains all moments at the same time. And that's what I'm going to do next time, and this is then going in the direction of Bernstein type inequalities. So in principle it's just following this idea that you're looking also on higher moments, and if you have information about them, they also give you more concentration, better information. Okay, but we do this in a much more compact way by considering all moments at the same time. If we go to the Fourier transform more or less, and then we can vary the argument of the Fourier transform, which means that the weights between the moments which we take into account is also we are free to choose the best situation. Good, but this we will do next time. And then the independence will, of course, getting more and more important, and also that we have this linearity. So, I mean, Chebyshev and Markov are quite general. So, for this For them, you don't need any independence. But next time we will have to use independence, because otherwise we have very general statements which are not so useful. Okay. Good. Yeah. So that's it for today.